As far as the very fundamental equation that relates the charges, because we've been talking about charges, to the capacitance is concerned, it's Q is equal to C times V. Now, I'm a big fan of deriving equations and learning things and teaching things from first principles. If we just distill this equation down to a very fundamental form, okay, and if I tell you that when I'm setting up this capacitor, okay, the more charge I deposited on the positive terminal, the more charge that I deposit on the negative plate, right? Do you expect that as the Q increases, right, the delta V between the two plates is going to increase? I think it's very intuitive. It doesn't require any leap in imagination to understand and recognize that the more charge that I deposit across these two plates, the more the voltage difference is going to be. One plate is getting more and more positive charges, and we are forcing it not to actually discharge it or not allowing these positive charges to actually jump onto the negative plate. And the other plate has a bunch of negative charges that are being accumulated, right? And as it happens, we are basically creating the delta V larger and larger and larger, correct? Now, those of you who work with these derivations, and if you go back to your high school physics and whatnot, one of the fundamental things that is always taught is that in order for us to change the proportionality sign to a constant, or to an equality sign, sorry, you actually have to introduce a constant. Okay, so let's introduce a constant, just call it constant. Make sense? And guess what that constant is? That constant is your capacitance. Because when you are messing around with this capacitor, okay, when you are increasing and decreasing the charges, and the voltage is increasing and decreasing, the one thing that remains constant throughout is the capacitance of this capacitor, which again is its ability to hold electric charge. And that's where this equation Q is equal to C times V comes from. And it can be a function of time, right? If you're talking in terms of a constant value, once a constant charge has been accumulated, there will be constant voltage across it. Then it just becomes Q is equal to CV. But if it is changing as a function of time, it is QCT is equal to C times VCT. Make sense? Now, in the last few minutes, I hope that you guys agree that I have not assumed any prerequisite knowledge, essentially any convoluted or very deep insights, right? We are working step by step, right? Creating the capacitor, defining what it physically is, and then evaluating how it is storing charge. And that charge is resulting into voltage, and the ability to hold that charge is basically our capacitance. Okay, so this is the first set of equations that we get to see when we are dealing with capacitors. The other element to capacitor, as you can see, is its shape, its dimensions, and some of the geometric parameters. And that's where the second equation comes into play. Both of these equations show up in the FE electrical as well as the P power reference handbooks. Okay. Now, this is purely geometric. This particular equation doesn't care about voltage, doesn't care about charges, nothing. This equation is defining capacitor as a function of the area of the capacitor, okay, and the distance between the capacitor. The more intuitive element over here is the area. So let's start with area. Let us assume that I give you a very small wafer, right? Two small wafers, and I tell you that there is air in between them, and then you can load as much charge on them as you like by connecting them to a voltage source. Now, intuitively, practically, realistically, if you think about it, and if you consider charge Q, right, let's say electron, this is the charge of an electron, and we consider electron as a matter particle, right? If the real estate is small, if the space is small, there will only be so much Q that can be accumulated, right? These are small minions that are placing themselves on the positive plate and the bottom plate. At some point, they'll run out of space and they'll start throwing themselves off the cliff. Correct? Make sense? But if we actually increase the size of this plate, correct, on both of these plates, now what is going to happen? You can have a lot more electrons deposited, the positive and negative charges. A lack of electron is a positive charge, a hole basically, but we can have a lot more of these charges deposited, correct? So you can see that the capacitance, which again, remember, is the ability of a material to hold charge, is directly proportional to A. Okay. The distance piece is a little bit intuitive, but the interesting thing about the distance is that as the capacitance is related to the voltage, right? Now, as you can see, if I increase the distance, okay, then the electric field strength is basically going to reduce, right? If these positive and negative charges are close together, the electric field is really strong. As I move them away, okay, then the electric field is weakening, right? So you can think about the distance from that standpoint. The closer the distance is, the stronger the electric field is basically, right? And the farther the distance is, the larger the distance is, the weaker the electric field is. And whenever we have proportionality, so inversely proportional to distance, directly proportional to area, remember, whenever we change the proportionality sign to an equality sign, we introduce a constant. And the constant in this case is permittivity of the material. Okay. Permittivity of a material is equal to the permittivity of free space, which is a constant, multiplied by epsilon subscript r. And when we loosely say dielectric strength, that's the number that we are referring to. As I explained previously, this number is simply a multiple that is applied on epsilon naught. It is a constant value, epsilon naught, which is a permittivity of free space. If there is nothing in here, then what is the dielectric strength that is being offered? That is a number, it's a constant, okay? And epsilon subscript r is how many more times we have higher insulation as compared to free space. And that is what we call as dielectric strength compared to the vacuum. And these are constants. So from a geometric standpoint, if you have very large plates and they're very close to each other, maintaining a very strong electric field, the capacitance will be very high. If you have very small plates and they are worlds apart, right, you basically don't have any ability to hold charge between them, right? Because there is no capacitance as a function of the area, as a function of the distance between them. And that's what's summarized over here. Okay, so this is looking at capacitance from the standpoint of the dimensions. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE Electrical and PE Power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE Electrical and PE Power exam preparation programs, please visit my website, studyforfe.com.